Now I come to a completely different analysis. It's about the forecast errors. Because in grid operation, the reliability of forecast is an issue. The better you know what will happen the next day or within the day, the better you can plan the unit commitment, and reduces also the cost for balancing. What we compared was these two extreme scenarios, the one in all-in-one place scenario and the uniform distribution. We analyzed two kind of forecast, the 1 hour ahead forecast and the day ahead forecast. Comparing the case of the all-in-one place distribution to the uniform distribution, you see a tremendous decrease of the forecasting errors. That means a wider spread of installation capacity also tremendously increase the reliability of the forecast. In the case of the intraday forecast, it's factor 6 between that. That also means you need less balancing power or reserve power to level this forecast errors out, and that's also a matter of economics of the system operation, and so also a matter of costs of the a matter of the total electricity costs. In the next step, we calculated a sort of levelized cost of electricity, but relative to a reference plant. What we first did was to assume some costs for the different turbines. So we stated that a turbine for low wind sites is 25% more costly than for good wind sites, but the investment costs only is about 80% of the capex cost. So that means that, well, the turbine 5 will be about 20% more expensive overall than the turbine 1. So we calculated a map of all the costs. On the second path, we selected a reference turbine. We selected a turbine of type 1, which represents a load factor of 0.3, which guarantee a good economic viability, and we scaled all the pixels to this reference plant. Combining the revenues which are represented with that to the costs represented by that, we ended up with this cost map. You see it here again. Well, red means the cost of electricity in this pixel is about 25% higher than the reference plant, which is which is located there for that example. And you have even some very good wind sites where the cost of electricity are even below this reference plant. But looking at the color, the impression of the map, you see most of the country is in the range till this reference plant. So, and even you can operate wind parks also at the late stage economically. That means also from an economic perspective, you have the most of the South African landmass can be used for economic viable wind energy projects. So the results, just for the slides I presented, was in South Africa you have enough space, extreme good conditions, nearly in every place you can have good viable projects. You have tremendous high load factors, but from a system perspective, it's good to use all these aggregation effects, which can be easily used, spread the installation over the country. 20 to 30% of renewable energy share on the total annual demand will not increase the short-term RAM significantly compared to the case without any renewable energy. The more distributed the wind turbines are installed, the better the aggregation effects are. Well, coming to the next case study, the curtailment analysis. In fact, it was a question of ESCOM, because often they get some, they have doubts about how much feed-in can be allowed at a substation. It's 100% of the nominal transformer capacity. It's more, it's less. So we did the following analysis. One means let's the case of the transformer capacity. We have different scenarios of feed-in. For example, that one, which have sometimes twice the feed-in than the transformer's capacity is, and we get some rules from ESCOM how to curtail the energy in such a case, because they say, well, for a single moment, an overload of up to 20%, it's possible, but not more. But it's not allowed that this overload lasts more than 45 minutes, I think. So we generated, according to this, the curtailed feed-in, which looks like the red curve here. This we did for every single substation in South Africa. We did it for an equal share of 50% installed PV capacity and 50% installed wind capacity. So in total, renewable installed capacity of one would say, well, the installed renewable capacity is equal to the transformer capacity. What we did is just counting how much energy for different penetration level has to be curtailed for this different cases. On this axis, you see the curtailment. 5% means 5% of the annual energy is curtailed. 10% would mean 10% of the annual energy is wasted. In this graph, we just considered the wind and PV feed-in and say, well, there is no load at that substation, just feed-in. So here we see, well, the first occurrence let some energy, about 0.5% have to be curtailed, occurs at 120% of the nominal transformer substation capacity. But there are also some substation where it occurs the first site at 150% of the transformer capacity, depending on the local conditions. The black line is the average value. So now you can, how to read this, if you say, well, a 5% curtailment would be okay, you can say, well, then I can, in average, I can have about 50% more installed capacity, wind and PV capacity compared to the substation's capacity. So as we know, at nearly no substation, we have only feed-in, but we have also some load. So we scaled the nationwide load to every substation. We scaled it equally to all of them. in fact, for a more detailed analysis, it would be nice to really use the load at the grid nodes. But for that study, we took one shape. Doing that, for sure, we have now the feed-in first covers the demand at these substations, and now we see, well, the first occurrence of curtailment will be at 170% of the substation's capacity. That means if you would have a 100 megawatt substation, you can install 85 megawatt of PV and 85 megawatt of wind capacity, and you will not see any curtailment. Well, this table summarizes this all. Here you see, well, the different curtailment levels, 0, 5, and 10% curtailment per year, only feed-in, and down there the feed-in and load, so the residual load, and you see, well, if you do not allow any curtailment, you can overload the substation by 20% or by 60% if you consider also the load. So that is all I want to say about the results of the study, and I'm glad to hand over to Tobias to draw the final conclusions and the outlook.
Well, thanks Stefan and team for presenting the results of the study. Just in summary, I think what we've learned from the results that we have seen in the last hour is first of all we've basically shown and we've quantified that a large amount of the South African landmass has economically viable wind potential. In fact, it's actually more than 80% of the South African entire landmass that has enough wind resource for relatively low cost wind energy, where you can get more than 30% load factor. What that means is that the magnitude and the cost competitiveness, also in terms of size and in terms of economic viability of wind power in South Africa, is on par with that of solar power. For solar, we know it now for quite some time, but for wind, I think it's the first time that we are quantifying that and showing that. The renewable energy development zones are definitely a good starting point. We saw that in a number of the aggregation scenarios, in the REDS aggregation scenario, some of the key metrics are improving. However, when expanding the REDS further, I think another key outcome of the study is that the wind resource should not be a limiting factor, but the environmental considerations in developing the REDS further is the more important consideration that should be taken on defining new REDS areas. The short-term fluctuation in aggregated wind power largely reduced through wide spatial distribution. It's not a surprise from a qualitative perspective, but I think when we look at the quantification, that's quite impressive. Up to 50% energy share of provided by wind would not increase the 15-minute gradients in the residual load if we distribute these 50% energy share wind turbines across the country widely. Increasing the area of wind energy application lowers the correlation of feed-in and ramps and smoothes the accumulated output also significantly. What we also saw is that we have very low seasonality of both wind and solar feed-in. That is a significant difference to many countries, not only Germany, but most countries that have installed large amounts of solar and wind, where they, because they are at higher latitudes, exhibit much higher seasonality in the solar supply and also in the wind supply. In Germany, that's at least luckily for Germany, is you have some negative correlation between wind and PV, where you have more wind in the winter and when the sun is not shining. But generally, it's not an ideal situation if you have a lot of seasonality and you have months where you have no output and other months where you have very high output. So low seasonality is definitely good from a system integration perspective. The forecast error also improves with widespread spatial distribution. We have quantified that. And from the substation perspective, we saw that now just in the last slide. 20% additional rated capacity should be possible at any substation without any curtailment. Some substations even higher than that. And if you allow 5% curtailment, then you can install 40% more than the rated capacity of the substation. Now that analysis is a starting point for subsequent further studies, because of course at the end of the day it's all a cost-benefit analysis. Does it make sense to curtail the wind PV energy, or does it make sense to upgrade the substation, or does it make sense to go somewhere else for the additional wind and PV power plant? If overall, to wrap up the entire results, I think what the study has shown or laid the basis for, the foundation for, is that South Africa has perfect conditions to introduce very large amounts of variable renewable energy sources, which is namely wind and solar PV. It's the only two variable renewables that we have. They are already at very low cost. We know that from the bidding windows of the Department of Energy, that both solar and wind can be deployed at low effective tariffs. Very low seasonality, widespread the widespread interconnected power system place that we already have, not for reasons of wind and solar PV, but it's there because the country is so widespread. But it now helps us in integrating spatially distributed resources into the system. If you compare that with Denmark, for example, which is almost like, I don't know how many pixels in our analysis Denmark would cover, but it's probably a handful. The aggregation effect is completely different. There you have to rely more on your neighbors, but then you have a cross-border exchange, and not everything is perfectly integrated yet in Europe. So we basically have an integrated European-sized system, all managed by one and the same system operator, Eskom, which helps. Yeah, and we definitely have enough space. That's also clear after the study. I think there were still questions whether the country has actually enough space to produce enough renewable energy to supply the country. That can clearly be answered with yes. In terms of outlook, I think what do we do next now? I mean, this study is a very good foundation. It has produced a lot of data, a lot of conclusions, results that improves our knowledge about renewables. But what do we do next? Well, first of all, sorry, do I get rid of this? Okay. This study can now be the basis for further research in how do you now actually, I mean, it's good to know that this aggregation effect helps and that you can smooth out the volatility, but what is the next step now? Like one important aspect is we are doing research, or we will do more research on the creation of virtual power plant platforms. Like how do you now, with this distributed nature of different supply sources, how do you orchestrate them as an intermediary layer between the individual power stations and the Eskom system operator, which is on the highest level and pulling everything together. But it's unlikely that the Eskom system operator will manage thousands of individual power stations individually. It's probably more suitable to introduce an intermediary layer, kind of an aggregator in form of virtual power plants. Then what is also important in terms of forecasting, we know that the forecast error for wind specifically will go down with higher spatial distribution, but we need to develop forecasting models for the country. This is not something entirely new. There's a lot of knowledge out there in the world in terms of how to forecast both wind and solar supply. But I think we need at least one, probably better 2 or 3 providers of forecasting models in the country that are South African based, and that I'm looking at universities, I'm looking at the CSIR itself, ourselves, we'll look into that. I think it's an important capability that we have to create in the country. Another question, when you go into very high share with variable renewables, is how much can the renewables themselves provide and supply reserve capabilities. If you think of especially the PV supply is very predictable, very smooth throughout the day. So if you know what's happening with the PV supply during the day, then you can use the PV fleet and instantaneously curtail it to the needs of the system operator. That's the provision of of a so-called negative reserve. You could even go as far as to say, well, I'm running my PV fleet at a curtailed mode of 2% all the time, of course wasting a lot of energy, but if the PV energy is cheap, then maybe that cost of doing that curtailment is now lower than the value of having instantaneously 2% of the PV output available for positive reserves. But that's something that has to be investigated a bit more in detail. When we look into the even further future, because all these concepts are not really new, we just have to apply them. When you look into a bit further future, and you look at this excess energy that we see, now you can use that, you can curtail that excess electricity, you can put it into storage, into batteries, or you can make a link between the electricity sector and the transport sector in producing synthetic liquid fuels or gaseous fuels, natural gas or methanol, diesel, petrol, whatever, any hydrocarbons from the electricity being the provider of the energy content, and CO2 that you have to harvest from wherever. That's an open question, by the way, in a world with lots of renewables in the system, with CO2 combined with renewable electricity giving you synthetic fuels as output. And now, why we are putting that here is something important for South Africa to consider for two reasons. If there's a global market for synthetic fuels that are then carbon neutral, because you don't have any fossil C in the fuels, if there is such a market, then there's a handful of countries who are predestined to supply that market. They're the countries with the lowest solar and wind renewable electricity, of which we are one. In addition to that, because the cheaper your renewable electricity is, the cheaper will be your synthetic fuel. That's one reason, and a number of countries have that advantage. We have, in addition to that, a very large chemical process engineering industry in form of Sasol that already knows how to produce synthetic fuels in very large quantities. So that gives us kind of a head start, first mover advantage over other countries with similarly good solar and wind resources. So we see that as a window of opportunity for South Africa to go into that direction. And then, of course, what we haven't really done yet in that study, but it provides the basis for further investigations, is to find the optimal mix between solar PV and wind supply, depending on what you want to optimize. Now, that's the first question, what is your objective function? But what is actually the optimal ratio between wind and PV installed capacity? Then clearly the study that we have now done for South Africa, I think would be very useful to expand that into the region, into the Southern African Power Pool, to cover with the same approach and with the same logic. And last but certainly not least, we will make the entire, of course, the presentations and the report publicly available, that's for sure, but we'll also make all the data sets, including the 4 terabytes of data of feed-in for 50,000 pixels across the country. We will put that on a platform for download. Bear with us if it takes some time. Because of the 4 terabytes, we are not sure yet how we manage that. But the idea is at the end that you can go to a map of South Africa, you click on a pixel or you type in your address, and then you are able to download the data for that 5 by 5 kilometers square and do your own analysis, or download it in aggregated level, whatever. We are looking into that, but that will come. With that being said, well, thank you very much for your attention. Thanks to the whole team for the outcomes of the study. I think we are at the end of this day. Presented the results of our work over the last year to you. I find that when I saw most of the slides the first time also last week, so it's really a lot of the stuff coming out of the press. I find it quite exciting. I hope it sparked some level of excitement on your side as well. Would like to thank you very much for your attention, that you bared with us for the whole day. Would like to offer an open invitation to stay in contact with the team, reach out to Crescent if there are additional questions or suggestions. If you sleep over what we now have and you know what's coming, what type of data is available, if you see something, studies that could be done or that could be useful, help us to guide this whole thing. I think we are all kind of new in this space. So that's just an open invitation to stay in contact and to help us to guide in the correct direction. But with that, I would just like to thank you again for your time and have a good way back home. And thank you very much. Bye.